Greetings, this is Dr. Mike Zuckery, and today we're going to talk about how correlation is not causation. Perhaps that's a phrase you've heard before. It's very common in science. So the first question we need to ask ourselves is, what is correlation? And it turns out, for our purposes today, we're going to talk about how correlation is the linear relationship among two variables. So imagine we have these two variables, x and y, and we have, let's say x is measuring creativity and y is measuring intelligence. And these are the numbers we have for four people. One person scored 2 on the creativity and 14 on intelligence. These are just made up numbers, of course. And the next person had a 3 and they scored 18 on the intelligence test. 4 and 5 being the next scores on creativity and associated with 12 and 8 accordingly. So sometimes we'll do what's called a scatter plot of this data. So if we just look at one example of this, right? So we have the x-axis, 1, 2, 3, 4, 5 going across the bottom, the horizontal. And then we got the y-axis going 5, 10, 15, 20. And so this point here would represent the first person who scored a 2 on the creativity score and a 14 on the intelligence score. Now let's get rid of those numbers right there and add the next one, which was 3, 18. If we try to fit a line to two data points, what you'll find is that you always get a perfect correlation, because you can always put a line through two data points. That's not very useful or meaningful to us. So let's erase that for a second and let's put those 2 points back on. So 2 and 14 and 3 and 18. And now let's add 4 and 12 and 5 and 8 and try to fit a line to that. And this is essentially a scatter plot. This is what a correlation is trying to do. It's trying to essentially fit a line of data as best it can to describe the data. And as you can see, there's some space between some of the dots and the line, and there's one dot that the line goes directly through. If you went through if the line went through all the dots, then that would be something called a perfect correlation, which we'll talk about in the next slide. So correlations can range from -1 to +1. And here we go. Let's just see the next slide. So imagine this one. We have an x and y. We have these dots going across like so. We fit a line through it and it goes through all the dots. It perfectly describes the data. This is what we would call a perfect positive correlation, and it would have a value associated with this +1. Now if we do this the opposite direction, you see something that looks like this, this would be something called a perfect negative correlation, and it would have a -1 value associated with it. So correlations can range from -1 to +1. +1 would be the example on the left. -1 would be the example on the right. So if x was creativity and y was intelligence, then on the left, the perfect positive correlation, it would mean that as you got your creativity scores go up, so it was perfectly lawfully linked, linearly linked to your scores on intelligence. So if we knew your x score, your creativity score, we could perfectly predict your y score. We could say the same thing on the other side, but the interpretation would be a little bit different. On the left, with a perfect positive correlation, it means as creativity goes up, so does intelligence. But you get the opposite on the other side. As creativity goes up, intelligence goes down. So now I want you to imagine that we run a little bit of a study, and we get this kind of picture of all those dots that you had there, was all in that pattern. You can see there that this line or that line could equally well describe the data, but not very well, and maybe this line or that line as well could explain the data. This is an example of a case where you have no correlation, no linear correlation. It turns out that it gets a little bit tricky too. You could have a perfect lawful or curvy linear relationship, but if you're trying to describe the data with a line, you'll end up with a zero correlation in some cases, even when there's a different picture, very different picture than what we see here. All right, so imagine this situation. On the x-axis, we're going to measure greenness of grass, and on the y-axis, we're going to measure the number of birds. And let's imagine we find something like this. Pretty much positive correlation between the two, meaning as the number of birds goes up, the greenness of grass goes up. As the greenness of grass goes up, the number of birds goes up. So now a question for you is, what's a potential explanation for this, right? So why, as the number of birds goes up, is the grass getting greener? So we're gonna talk about possible causal explanations, even though we know from the very title of this correlation is not causation. So I'll give you a couple of seconds here. You can see that clock run off really, really quickly, not enough time. But what are some potential explanations that the number of birds could cause grass to get greener or vice versa? So take a second, think about that, and then here, imagine this, right? So if you got a lot of birds coming out, it's a beautiful bird, and that's pooping. The more birds you have, the more poop you have, the greener the grass could get, because poop can serve as a fertilizer, right? That could be a causal explanation for how increasing the number of birds increases the number of grass. But if you go the other direction, maybe if we have really green grass, maybe there's a lot of bugs there and worms. Those are supposed to be worms. If you have that situation, maybe the greenness of the grass is actually attracting the birds because they know that there's going to be a good food source there. All right, so that's a directionality problem, right? We don't know whether the greenness of the grass is causing birds to show up, or the number of birds and their poop is fertilizing the grass so it's becoming greener. Of course, they could be causing each other, right? You could have mutual kind of bidirectionality going on. That's a directionality problem in correlation. We don't know what's causing the other, and if it's not part of an experiment, we really can't say that we found any causality, actually. The other problem is one called the third variable problem. We've measured two things and we found a relationship between the two of them, but maybe there's something else that we haven't measured that's affecting both of these. Maybe if you give a couple of seconds here, maybe you can think about what that might be. So what might be something we didn't measure that's influencing both of these, and it's just an illusion that the two are related to each other. That could be a possibility. Maybe it's true that there's those causal explanations, but maybe not. If you came up with seasonal changes or weather, right, as the seasons change, that affects the number of birds. It also affects the greenness of the grass. All right, so if you want to establish causality, you got to do something. You have to do more than just look at two variables and see if they are related to each other in some sort of linear way. And to do that, you need an experiment. So just as an example, you need to split the word world into two meaningful things. Imagine that you have two universes that are exactly identical. We change one thing in one situation, and we don't change anything in the other. So the classic example here could be the Clever Hans, where Clever Hans was a horse that supposedly could spell your name out, tap out answers to responses, know what time it was, all this kind of stuff, add and subtract, all these kinds of things. But in this one experiment that an individual named Funks did, he just basically had people look at a number and say, okay, Clever Hans, what's this number? That's with knowledge. Or they didn't look at the number and then they asked Clever Hans what the answer was. And it turned out that Clever Hans was about 90% correct when you knew the answer. But if you didn't know the answer, Clever Hans was right about 10% of the time. So he was really picking up on subtle movements of the person asking the question, little unconscious movements that the person didn't even mean. So you need a manipulation of some sort, and then you need to see changes over time. You have to have measurement. In this case, it was how accurate was Clever Hans. We call the manipulation our independent variables, and we call our measurement dependent variables. So it turns out that you can really only establish causality with an experiment that has at least these sorts of components. Now, this is one last little nuance, and try not to let your brain just explode from this, but you could use correlation as part of an experiment to get at causality. So, for example, if correlation was your dependent variable, and you did a manipulation where you tried something new versus the presence of something versus the absence of something, and if the presence of the manipulation causes changes in the relationship between two variables, that could be a way to get at causality. But without manipulating the world and without measuring it and without seeing changes over time, you really can't get at causality. Thanks for listening, and that's it.